All right, good morning. Happy Chem Friday. It's the end of our week in chemistry. Well, not quite, because you do have homework and quiz due this weekend. But hopefully you'll find that manageable. Again, can we get started, please? Thank you. Homework and quiz go up through chapter 3, so we have finished that material, so you should have most of the information you need to do well on those assignments. If you do need more practice, there is that adaptive quiz. Again, that's for practice. It doesn't count for your grade, but it might give you a good idea of where you sit in chapter 3 material. Office hour today, don't forget about bonus points for that. For those of you who'd like to plan ahead, our first exam is in 2 weeks from today. Okay, so we'll have an exam on Thursday, 2 weeks from now. Starting next week, I will start posting some practice material for the exam, a short study guide, some practice exams, things like that to help get you ready. Okay? Any questions before we get started on material? All good? All right. Let's see if I can get this to work. We've been talking about subatomic particles, protons, neutrons, and electrons. Do you have 11 protons? Because you are sodium fine. I got a few laughs for that one. That was pretty good. Okay. Took a while, huh? All right. Let me remind you about Achieve. Obviously, you guys have been in there and whatnot. This is my layout, which is a little bit different from yours. So let me just switch to the student view. Again, I think the best way, there's different ways to view things, but the assignment view is the best way because it has it in order. So you'll see there's a lot of stuff that's still listed for this week. Homework and quizzes were already due. You can do those late, okay? The other thing to note is if you do those and you get like 90% done, 90% of the problems done, you will get full credit for those if you get those done on time. And then if you do like a few problems late, the late points are just for those last problems that you turn in late. So those are still open. You can still get credit. If we keep scrolling down, I sent out a note that I posted the chapter 4 lecture slides, so those are there. There's homework number 2. This is one thing I don't like about the system. I can't schedule what the week is. I'd like the week to be Monday through Sunday. So Saturday falls in this week when the homework is due. Sunday falls into next week. So make sure you're aware of that. They do scroll together for you, hopefully. So there's next week. I've gotten a little bit ahead. If you want to work ahead, I have the next homework posted, which is, we're going to start chapter 4 today. So that's the next one. And there's also an adaptive quiz on chapter 4. So there's some things posted for later. And then, of course, here's all your past assignments that are more than a week old. Okay? Let me go back to my view real quickly. Maybe not so quickly. Just want to show you some of the data I get. So this data on the left side of the screen, that is homework number 1. Tells me the average time. It took you guys about 2 hours on average to finish homework 1. I think that's a pretty good amount of time. You can see the average is almost 98%. That's really good. So keep up that good work. And you can see, you know, some people spent, I think, as little as 40 minutes maybe on the assignment, and some spent as much as 4+ hours. So good on you to those who spent like 4+ hours. Way to work at it. That's what it takes. I mean, you can see some people spent a lot of time, but they did get 100% on the assignment. So keep working at this stuff. Hopefully it'll help you learn the material. All right. One more comment before we start. We are 3 weeks into the semester, which in some ways almost surprises me because I kind of thought we'd all come back, COVID would break loose, we'd be remote by week 4. That's not the case yet. So don't get complacent. Please wear your face masks in class. Please wear them properly. You do need to cover your nose. So let's keep doing this. It'd be cool if we could be in person the whole semester. So let's keep chugging along. See how this works. All right. Before we get to chapter 4, does anybody remember this? Oh, I got to do attendance. Don't forget to sign in. It's coming around the room now. Does anybody remember this? This is where we kind of started the semester. Okay, so now you've learned some chemistry, hopefully. All right. So again, this is an atomic force microscope. These were invented, kind of late 1980s. This is a more advanced one in that the tip of the probe has a carbon monoxide molecule on it, which allows greater sensitivity to the electron density of the surface. Here's an image of a molecule. That molecule is called hexabenzochoronine. And there's a big question for you. And we're going to do the first 3 parts right now, because I think we have enough information to do that. So there's hexabenzochoronine. The structure of the molecule is evident, but the types of atoms are not identified. What atoms make up the molecule, and what are the empirical and molecular formulas? Now, we haven't gotten to empirical and molecular formulas, so we're going to save that part. But let's get to part A. It's composed of atoms of 2 elements. The most abundant isotope of one element contains 1 nucleon in the nucleus, so 1 particle in the nucleus. And the most abundant isotope of the second element contains 12 particles in the nucleus, 12 nucleons. Identify the atom. So take 30 seconds, turn to your neighbor, and see if you can identify those 2 atoms. You might want to look at a periodic table. And I do have a couple more of these left if you do not have these, but I only have like 4. So these were passed out at the start of the semester. So look back through your notes to see if you have them. You're welcome. Last one. You're welcome. All right, so what's your conclusion? What are the 2 elements that make up that compound? Hydrogen and carbon. Okay, so a hydrogen, the main isotope of hydrogen, look up at your periodic table, atomic number of 1 proton. Okay, so together we call protons and neutrons nucleons. Those are particles in the nucleus. Okay. So main isotope of hydrogen, 1 proton, no neutrons, just 1 nucleon. Okay, the other isotope has 12 nucleons. So then you kind of start looking down the periodic table. You get to carbon. You see an atomic number of 6. That tells you 6 what? Protons. And then you see an average atomic mass close to 12. Which probably means the most abundant isotope is carbon-12. meaning that that would also have 6 neutrons. Okay, so 6 protons, 6 neutrons, mass number of 12. Okay, everybody all right with that? So we've learned some chemistry, right? Okay, so this molecule is just carbon and hydrogen. Let's go to the next part of the question. Let's see. Well, I guess we can only do the first 2 parts. I was thinking we could do 3 parts today, but let's just go to part B. So we know the atoms. Now let's calculate a percentage. So there is a problem. We haven't talked much about percentage in here, but you should have done percentages at some point, and there is a question in this week's homework that does ask you to calculate a mass percentage. So let's look at that now. Okay? So we have a 5-gram sample. 4.826 grams of that is carbon, the element with 12 nucleons. Okay, I didn't write carbon there because I didn't want to give it away. Determine the percent by mass of each element. All right, so let's do that. Okay, so just in general, a percentage is the part you're interested in, divided by the whole amount, part divided by the whole. That gives you a fraction or a decimal, and then you multiply by 100 to get a percent. So in this case, the part we're interested in is carbon. The whole mass is the mass of the sample. And we multiply by 100 to get a percentage. Okay, so do that calculation very quickly. How many sig figs? 4. Okay, so we're dividing, both of these numbers do have 4 sig figs, so we carry 4 in our answer. Okay, so 96.52% carbon. All right, and that shouldn't surprise you. It's only a 5-gram sample, and you can see that over 4.8 grams of that is carbon, so most of the mass, the percent by mass is carbon. Now you could do 2 things here. You could do the same calculation for hydrogen. The mass of hydrogen divided by the total mass, multiply by 100 to get a percent. Or, since there's only 2 elements, what's the easier way probably at this point? Subtract from 100, because the 2 masses should add to 100%, since there's only 2 elements. So percent hydrogen will just be 100% minus 96.52%. And what does that give us? 3.48. Did I do that right? Questions? All right. So this is, we haven't gotten too far in this problem. We're going to use that mass percent data. Probably going to be a while in the semester because we're going to still kind of focus on the atom, but we'll eventually come back, use that data to figure out the formula of the compound, and then a few other things about it. All right, any questions before we move on? Yes?
So for that one, we know that it has 3 sig figs because of the 100%.
Yeah, well this one, this 100% would be exact. We could write 100.00, but we're assuming, since there's only 2 elements, their percentages should add to 100%. And then since this number has 2 digits after the decimal point, and we are subtracting, we go by the decimal point. So we're going to carry 2 digits after the decimal point in our answer. Okay, but yeah, it probably would have been better if I had written this number. Let's do this again. Let's write that. Sorry, didn't write that very clearly, but 100.00 to indicate that we at least have that many sig figs. Other questions? All right, hang on to this problem. We will actually continue and finish this at some point in the semester. All right. So we are pretty much going to cover, I haven't taught Chem 130 in a while. I teach general chemistry all the time. This normally the 2-semester course. This is just kind of a 1-semester condensed version, but I've never used this book before, so I kind of thought we should just go in order. So what we're going to do now is we're going to dig into the atom a little bit deeper. Okay. So far let's just back up and kind of review. We can go way back 2,500 years ago where the concept of the atom was first proposed. And then that kind of disappeared for a couple thousand years. And then that concept came back. Some really cool early experiments that we talked about. Dalton then came along and tied that all together into unifying atomic theory. And then very recently we looked at what I think are some of the coolest experiments related to atomic structure, the cathode ray tube experiment by Thomson, Rutherford's experiment, and Millikan's oil drop experiment. Okay? So the cathode ray tube experiment basically proved electrons exist in all matter. Thomson also figured out the charge to mass ratio. Rutherford proved there was a nucleus, a small, dense, positively charged nucleus. And then Millikan actually figured out the charge and mass of an electron. So all really cool stuff. So in this chapter, we're going to probe more about where the electrons are. And to do that, we have to know a little bit more about light, okay? Or what we call the electromagnetic spectrum, okay? So visible light is a very small part of the electromagnetic spectrum. Okay, it's kind of in the middle. We'll talk about frequency, wavelength, all that fun stuff. Okay, but visible light is kind of in the middle of the spectrum. And then we have things like ultraviolet rays, infrared, radio waves, TV waves, X-rays, gamma rays, things like that, microwaves. Okay, so you've heard of all of these. Those all have similar properties. Okay, they're all electromagnetic radiation. They travel at the speed of light in a vacuum, and they all have an associated motion that has a wave-like motion, and we'll talk about that as we go along. Okay. So these are just some pictures. Our world is immersed in light and soaked in color. Well, that's interesting. Okay. So let's focus on light. What is light? Okay, we call it electromagnetic radiation. It is a form of energy. Okay, and we'll actually calculate the energy of, say, visible light or UV light or something like that. Okay, and we talk about how it travels in waves and what we mean by that. Okay, so hang with me here for a second. So electromagnetic radiation, so look at that first word, electromagnetic. There's an electric field component, and perpendicular to that, 90 degrees, is a magnetic field component. So let's just focus on the electric field component. That component is going positive, negative, positive, negative. It's changing polarity very, very quickly. Okay? So it's oscillating. Okay, positive, negative, positive, negative. But it's also moving through space. Okay? So take this oscillating charge as it moves through space, and then we see it has a wave-like motion. Okay? So that oscillating charge, or there's also oscillating magnetic field as well, moving through space, wave-like motion. So now we can describe its properties in terms of a wavelength. Okay, what's the distance between those waves as it propagates through space? Okay, how many waves do we have per second? That's its frequency. Okay, so frequency and wavelength are two ways that we're going to describe the property of electromagnetic radiation. We're also going to look, kind of like we hinted at recently, that electrons have wave-like and particle-like properties. We're going to see the same thing for light. So sometimes we're going to talk about particles of light, not waves, and those particles of light we call photons. Call them photons. Okay. So hopefully before today is over, we will actually do some calculations with frequency, wavelength, and energy. But let me show you the spectrum first. Okay. So there's visible right in the middle. It's a pretty small part of the electromagnetic spectrum. It's the only part we can see with our eyes. Okay. And you will notice what we describe as the colors of the rainbow, right? So red, orange, yellow, green, blue, indigo, and violet going across there, okay? So we're starting on the low energy end on the left, high energy end on your right, okay? So radio waves, TV waves, things like that are pretty low energy, even microwaves, okay? Now you might think microwaves are higher energy because we use them to cook our food, but microwaves happen to be the right energy to rotate molecules. And in particular, in our microwave ovens, we rotate water molecules. And these water molecules get spinning really fast, and essentially it's a frictional type heating that heats up our food. So if you try to cook dehydrated food, heat up dehydrated food in your microwave, it doesn't do a very good job. You need some water there. Infrared is heat radiation. You should be familiar with that. Visible after that, notice ultraviolet. Try to protect ourselves from the ultraviolet rays of the sun so we do not get skin cancer and all that fun stuff. Higher energy than visible. Probably know that X-rays are higher energy than UV rays. Okay, we use them to image bones and other structures in our body. And then you may or may not, you've probably heard of gamma rays, but gamma rays are very, very high energy electromagnetic radiation that are kicked out of the nuclei of some radioactive substances. Okay, for an unstable nucleus to lose energy, one thing they can do is just kick out some really high energy electromagnetic radiation. All right, so a couple things to note here. Low energy. Make a note of this, and we're going to talk about the relation between frequency and wavelength. Low frequency, which means the oscillations are slower, that electric field, and then because the oscillations are slower, it's going to be a longer distance between the waves. Okay? High energy, high frequency. A lot of oscillations of that electromagnetic radiation. Okay? It's switching positive, negative very, very quickly. So that as it moves through space, those waves are going to be very, very close together, short wavelength. Okay, so try to visualize this. If we have low frequency, okay, follow my finger. I'm going to try to hypnotize all of you. You guys ready? No, I'm just kidding. That was supposed to be funny. Okay. So low frequency means that wave, that electric field is oscillating slowly, but remember it's moving through space. So as it oscillates slowly, there's going to be a long distance between waves. And radio waves, does anybody still listen to the radio? Does Sirius count? Sirius XM? I don't know. I still listen to the radio, but you're talking meters distance between the waves. That's kind of the wavelength we're talking about for radio waves, okay? Now we get to gamma rays, oscillating so fast I could never even get close to trying to simulate that. But if this is oscillating very quickly, as it moves through space, those waves are going to be much, much closer together, short wavelength. So try to visualize the relationship between frequency and wavelength. High frequency, short wavelength. Low frequency, longer wavelength. Okay? So it's good to have that kind of mental picture. All right, and there's a zoom in of the visible, okay? Longer wavelength then, so make a note of this. Red is kind of 700, maybe out to 750 nanometers wavelength. So note the unit. The units are important. Know if you can see that very clearly there on the screen, but you see nanometers. So this is 700 nanometers. What does nano mean? What number? 10 to the negative ninth, so make sure you know your metric prefixes. So this is 700 times 10 to the negative ninth meters. That's a pretty darn small distance. If you want to go to micrometers or micrometers, that'd be 0.7 times 10 to the negative sixth, so what is that? We're talking millionths of a meter between wavelengths. Very short. But that's the longer wavelength end. So that's the lower energy end of visible. We're gonna, again, we'll spend more time with the relation between wavelength, frequency, and energy. But longer wavelength, lower energy. Shorter wavelength. Okay, so this is a shorter wavelength. Higher energy. Okay, and we will look at this in more detail as we go along. Okay? Now, an easy way to remember this, look what's lower energy than red. What do we call it? What's lower energy than red? Infrared. Okay, so infrared is lower energy than the red end of the visible spectrum. What's higher energy than violet? Ultraviolet. Okay, so you kind of have a feel that ultraviolet is higher energy than visible. So visible ends at violet. Now we move higher energy into the ultraviolet. Red is the lower energy end of visible, and then we move into heat energy, the infrared energy, which is lower energy than red. Okay, so try to have a feel for the energies of these different types of electromagnetic radiation. Okay, so we've already talked about wavelength. Okay, shorter the wavelength, higher the energy. Longer the wavelength, lower the energy. And again, think about this oscillating electric field. You could think magnetic, but we don't have to do both. But the faster that's oscillating, the closer they're going to be together. So that faster oscillation, that's the higher energy part. Slower oscillation, lower energy. Longer wavelength. Okay, I think I've done that enough. Okay, and there's the IR and UV I was just talking about. All right, if you want definitions to write down, I think they're pretty self-explanatory. We do need to talk about the symbols, though. Wavelength is, and I always joke, I like to joke. You might not like my jokes, but if you're an optimist, you measure from the peak of one wave to the peak of the other wave. If you're a pessimist, you measure from the trough of one wave to the trough of the other wave. I don't know. Anyway, you just measure distance from one wave to the next. That's your wavelength. Note the symbol up there. That's a Greek letter called, does anybody know what this Greek letter is? That is lambda. Very good. Thank you. Okay. And one thing that I think physicists have right is their symbol for frequency is F. In chemistry, we do not use F for frequency. Don't ask why. That actually is not supposed to be a V. It's also supposed to be a Greek letter that kind of, it looks like a V, but it kind of has more of a tail on the other side of the V. Does anybody know what Greek letter that is? Yeah, that is nu. Okay, so if you just write it as a V, make sure you realize it's not velocity. Okay, which is kind of why I don't like that as a symbol for frequency, because it kind of looks like a V and then you think velocity, but it's not velocity. We're going to use a different symbol for velocity of light, and you'll see that in just a minute. Okay, so make sure you know wavelength lambda, frequency nu, all right. Frequency, number of waves per second, we've been talking about that a lot. How many oscillations per second of that wave? Okay. You will also see, instead of, well, let's talk about units here. Sometimes, for frequency, you will see something written as cycles per second. Okay, how many cycles of that wave per second? Okay. Now, most of the time, we just leave cycles off, and we just use unit of frequency as per second. How many per second? So a lot of times, it's just 1/seconds. Okay. But another unit you're going to see for frequency is Hz, and that stands for hertz. So a scientist, early work on electromagnetic radiation, his name was Heinrich Hertz. He gets a unit named after him. Isn't that exciting? So again, hertz is equivalent to cycles per second, waves per second, or a lot of times we just use per second. Okay, so be familiar with that. I did not talk about wavelength, although we did mention it on the previous slide. Wavelength is a distance. Okay, so we're going to use for wavelength meters, nanometers, picometers, millimeters, depends on what region of the spectrum we are in. All right, any questions at this point? I want to get to some calculations. I want you to see these calculations are actually kind of fun. I like calculations. No questions? Everybody just chill today? All right. Oh, here's actually some different ways to represent that same unit. So if we were talking a frequency of 10,000 waves per second, okay, so 10,000 oscillations per second, seems pretty fast, doesn't it? Well, frequencies get even a lot higher than that, okay? So I always, when I'm really bored, I try to, we're gonna do a calculation, hopefully, and we'll get a frequency of like 10 to the 14th per second. So then in my mind, I sit there and try to think about, like 100 trillion oscillations, 10 to the 14th, 100 trillion oscillations every second. And I try to wrap my mind around that, just because I'm kind of weird that way. But, it's kind of hard to imagine. But 10,000 oscillations per second, we could use hertz, or we could just say per second, 1/seconds, which is the second one there. Or another way to write per second is seconds to the negative first power, or what we call reciprocal seconds or inverse seconds. Okay, so get familiar with the different units that we use. All right, and here's a key qualitative concept that we've already talked about, but let's write this down. Wavelength and frequency are inversely proportional. Okay, and what we mean by inversely proportional, high frequency, a lot of oscillations per second, short wavelength. High frequency, short wavelength. Okay, they're opposite. The higher the frequency, the shorter the wavelength. The lower the frequency, the longer the wavelength, inversely proportional. Now, has anybody seen this constant before? Speed of light constant? Yes? No? Okay. So all forms of electromagnetic radiation, whether it's visible light, whether it's gamma rays, whether it's radio waves, travel at that velocity, that speed, in a vacuum. Okay, now in real world, as light travels, it's gonna hit air molecules and other things, dust particles, and it's gonna slow it down. So we always, we're gonna use that number, but technically it's in a vacuum where there aren't other things to block that light traveling. Okay, but this is the speed of light constant. If you get bored and you wanna convert to US units, okay, just to give you maybe a better feel for how quickly electromagnetic radiation travels, if we convert to miles per second, okay, and I'm not going to do this conversion, but if you want to try it, that's 186,000 miles per second. Okay, it's pretty quick. So here's an equation, and we're going to do a calculation here with that equation. Speed of light constant is equal to the wavelength times the frequency. That's it. And let's see why that is the case. What's the unit of wavelength? What's the unit of wavelength? Meters. It's a distance, right? What's the unit of frequency? Hertz or per second. How many per second? So a lot of times we just write it as 1/2. So look at what units we end up with. Meters per second. Wavelength times frequency gives us speed, meters per second, speed of light. Okay? So nice simple equation. Make sure you make a note of that. That's the type of equation that I will put on the equation sheet of the exam. So you don't have to memorize it, but you probably will. But it will be there in case you forget. Oh, see, a lot of times I don't look ahead at the slides, and I just do what I want to do, and I end up with the same thing. All right. So let's do a calculation. Green light. Okay, remember the visible spectrum. Have a feel for the visible spectrum. It's about 700 on the red end, nanometers, wavelength. Red end, low energy. 400 nanometers on the violet end, higher energy, short wavelength, higher energy. Okay, so up 400 nanometers to 700 nanometers for visible. Green light's kind of toward the middle, 500 nanometers. What is the frequency of this light? Okay, so a couple things to keep in mind as you do this calculation. Let me actually write toward the bottom just so I don't write over things. Speed of light constant, 3 times 10 to the 8th meters per second. Again, I didn't mention, of course, we're using C for the speed of light. Okay, you don't have to memorize that, but I bet you will pretty quickly. That will be on the equation sheet as well. Try this calculation. Now, be careful. Watch your units. Just try this on your own for a minute and see what you can do with this. We have wavelength. So you have speed of light. You have wavelength. The only unknown in that equation is the frequency. But you do have to watch your units. Watch your units. And you can turn to a neighbor as well if you want to check how you're doing there. All right, how we doing? Not too bad? Okay. Some of the, we're not maybe used to Greek symbols sometimes in our equations, or maybe we are. But it's a pretty simple equation. There's only three things. Speed of light, that's a constant, so that's a given. Okay, that's not going to change. And then you have wavelength and frequency. All right. Now, since we want to solve for frequency, you might want to rearrange this equation ahead of time. You don't have to. You can plug in and then rearrange as you go. Or you might want to say, well, I'm going to divide both sides of the equation by wavelength. Wavelength will cancel out. And I'm going to write it down here at the bottom. Frequency is speed of light divided by the wavelength. Okay? All right, so here comes all this. Okay. So, one, I did say watch your units. Okay? So speed of light's in meters per second. Visible light, almost always when you express wavelength, the visible light will be in nanometers because the wavelength is pretty darn short. All right? So you do need to know that nano is 10 to the negative 9th. Okay, so know those metric prefixes. Okay, now here is a shortcut. We could set up a conversion and say 1 nanometer is 1 times 10 to the negative 9th meters and actually do a conversion. Or we can shortcut this. Okay, we have 500 nanometers. We know that nano, that letter, just means the number 10 to the negative 9th. Okay, so the shortcut conversion is just to write that as 500 times 10 to the negative 9th meters. And we can actually punch that in our calculators like that. Okay, so that's pretty cool. That's a little shortcut conversion. Okay, so as we did rearranging our equation, all we need to do is plug in the speed of light. We do need to convert the wavelength to match the distance in the speed of light constant. Now you will note that meters cancels. Okay. So as we punch in our calculator, don't forget to use the EE key on your calculator. 3 EE8. Okay. And then it sees that as one number, and we divide, and then just punch in 500 EE negative 9. And then enter. And what did you get? Oh, there it is. Here, let me write it so you can actually see it. Six times 10 to the 14th. Is everybody able to get that? Okay. And again, what kind of units? If you just look at what we end up when meters cancels, we just end up with 1 over seconds. We can also write that as hertz, or we could write that as seconds to the negative first power. All right, questions? Okay. Not too bad of a calculation, just watch your units. And you'll see that a lot in this chapter where you're going to have to convert units to make sure that they cancel. Okay. So the frequency of green light, look at that number. That's 600 trillion cycles per second, oscillations per second, 600 trillion. I can't wrap my mind around that. I try. I try to get there, but it's always kind of fun to think about. All right, We have about 3 minutes. Let's just do the qualitative piece here. We just did a calculation, so you have to be able to do the quantitative side, but let's do the qualitative side now. And the longer the wavelength, okay, the lower the frequency. And you can see that in this equation. Remember, speed of light is a constant, so that constant c is not changing. So if my wavelength gets bigger, my frequency has to get smaller if you're just looking at that equation. So, sometimes I'll do this, and I don't know if this helps. I'll put by wavelength. Let me choose a different color here. Let's do light green. So if our wavelength gets longer, larger number, okay, so up arrow meaning bigger, then to equal that same constant, frequency must become smaller. Okay, lower frequency. Longer wavelength, lower frequency to end up with that same constant. So if you want to think about it mathematically, you can, or you can just think about as I was, watch my finger, right? As we go low frequency, long wavelength, okay? High frequency, short wavelength, okay? So as frequency goes up, wavelength goes down, okay? So inversely proportional. Now, energy, we're going to look at an equation for energy next time, but always think about energy in terms of oscillations. If that electric field or magnetic field, both fields are oscillating very, very quickly, that's high energy. If it's oscillating slowly, that's low energy. Okay? So we're going to look at equations next time that relate energy and frequency and energy and wavelength. And they're pretty simple equations as well, but you got to make sure you realize as we go on, you need to know the quantitative piece, but you also need to know the qualitative piece. How do wavelength, frequency, and energy behave qualitatively? Okay? All right. God, another minute. I keep losing minutes. What am I doing here? It's Chem Friday. All right. Well, happy Chem Friday. Have a nice day. If you have classes tomorrow, have a wonderful time. I kind of like teaching Monday through Thursday. It's kind of fun. My teaching week, not my work week, but my teaching week ends on Thursday, which is kind of nice. Did everybody get the attendance sheet? Good. All right, if you have any questions, please come on down.